Hello lovers of chemistry, it's Chemigator. Welcome back to my channel. Today I wanna take a deep dive into the total synthesis of Lucidumone. This remarkable molecule features a complex polycyclic ring system, including a bicyclo 2,2,2-octane subunit fused to an indenone framework. Notably, the bicyclo 2,2,2-octane unit contains 6 stereocenters, making Lucidumone a highly challenging synthetic target. Lucidumone was first isolated in 2019 from Ganoderma fungi, a rich source of Meroterpenoid natural products such as cochlearol A, lingzhiol, and ganocin A. Since its isolation, various research groups have independently developed intriguing synthesis routes to access this complex molecule. In 2022, she and co-workers reported the construction of the pentacyclic core of Lucidumone in racemic form. That same year, Torres Group achieved the first enantioselective total synthesis of Lucidumone, employing an inverse electron demand Diels-Alder reaction followed by one-pot retro 4+2 cycloaddition sequence. In 2023, Kawamoto and Ito's group disclosed a fascinating racemic total synthesis of Lucidumone using a one-pot glycine rearrangement followed by an intramolecular allo reaction. They also describe an enantioselective version of the synthesis via a chiral transfer strategy in the glycine rearrangement. In this video, I wanna break down the latest total synthesis of Lucidumone recently reported by the Lee Group in 2024. So let's analyze the retrosynthetic pathway. The target molecule can be achieved from the hexacyclic intermediate, where the presence of a silicon oxygen bond in the ring led to the hydroxyl and carbonyl functional groups on the bicyclo-octane moiety through a sequence of Fleming Tamao oxidation, Wacker oxidation, and O-demethylation. The indenone framework and the 5-membered tetracyclic ring on the bicyclo-octane can be constructed via a sequence of O-deprotection, Prins reaction, and cycloesterification followed by oxidation. This key intermediate can be obtained through a Suzuki coupling between a boronic acid and a vinyl trifolate. Tracing this intermediate back, it can be derived from a compound produced via an asymmetric intramolecular Diels-Alder reaction of a precursor molecule. This precursor can be prepared from an easily accessible silyl acrylate imide and a corresponding diene. Now let's run through the forward synthesis. In the first step, we need to create the silicon-oxygen bond between the silyl acrylate imide and the alcohol. This reaction has an interesting mechanism. The addition of the first equivalent of trifolic acid protonates the carbonyl group of acrylate moiety. This protects the double bond from further electrophilic attack because the resulting carbocation is not stable. Next, the second equivalent of trifolic acid protonates one of the benzene ring's double bonds, disrupting aromaticity. The resulting carbocation then tries to restore aromaticity by pulling electrons from carbon-silicon bond, making it behave as a good leaving group. As a result, the trifolate ion attacks the silicon, and the carbocationic moiety leaves the molecule as a phenyl group. The isolation of this intermediate is not needed. So what's going to happen is 2,6-lutidine acts as a base to deprotonate the alcohol, allowing it to attack the silicon and form the desired intermediates. With this step complete, we are now set for intramolecular Diels-Alder reaction to construct the bicyclo 2,2,2-octane unit. Notice that this challenging skeleton is achieved by precisely assembling fragments of the starting material, where 6 carbon atoms result from the 4+2 Diels-Alder reaction. These 2 carbon atoms, which join the 2 ends of the diene, construct the bridge of the bicyclic core. If you are interested in how designing the right starting materials increases efficiency, check out this video, where I explain the importance of selecting appropriate starting materials in organic synthesis. The intramolecular Diels-Alder reaction should proceed in an enantioselective manner to correctly install the substituents of the bicyclic core. For this purpose, various chiral ligands were tested with different copper salts, and it was found that using this specific chiral ligand with copper trifolate resulted in the highest enantiomeric excess of the product. In the next step, this intermediate underwent hydrolysis to produce the corresponding carboxylic acid. On the other hand, reduction with lithium borohydride provided the alcohol. It was found that the neighboring carboxylic acid or hydroxyl group could direct the hydroboration at its carbon atom of the double bond, improving retrioselectivity. Treatment of the carboxylic acid with boron tetrahydrofuran followed by oxidation produced a diol product. Notice that the carboxylic acid was also reduced in this reaction. After protecting the primary alcohol, des-Martin oxidation resulted in the desired ketone along with its regioisomer. If the reaction started with the alcohol in the previous step, a mixture of two regioisomeric ketones was produced in a 1-to-1 ratio. This indicates that the carboxylic acid is a more effective directing group than the alcohol. In the next step, deprotonation of the ketone with KHMDS followed by the addition of phenyl triphenylmide produced the desired vinyl triphenylate. The palladium catalyzed Suzuki cross coupling between this intermediate and the boronic acid gave the tetracyclic compound. The next key step is converting this intermediate into the cage-like structure. This transformation is crucial because two rings are formed in a single step. It involves the protection of the alcohol followed by a Prins Cyclization and cycloepurification. Before attempting this on a real substrate, a model reaction was tested by removing the methoxy groups from the boronic acid. In this case, the desired product was successfully obtained in the presence of HCl. In the Prins Cyclization step, the aldehyde group is activated by the acid, allowing the double bond to attack the aldehyde and complete the construction of the indron moiety through an intramolecular cyclization. Next, the resulting carbocation is trapped by the oxygen atom, forming another 5-membered ring via cycloepurification. Without the methoxy groups on the phenyl ring, the desired product was obtained in 89% yield with a 20:1 diastereoselectivity. But this condition didn't work for the real substrate, leading to the byproduct dominating over the desired product. After screening various conditions with different Lewis acid, it was found that an excess amount of HCl at -78° led to the desired product, which was then oxidized using des-Martin oxidation. The reaction temperature and time had to be carefully controlled to avoid the formation of byproducts. In the next step, this intermediate underwent Fleming Tamao oxidation, resulting in a diol intermediate. Fleming Tamao oxidation is a useful reaction for converting a carbon-silicon bond to a carbon-oxygen bond while retaining the configuration of the carbon atom, and can be carried out in acidic, neutral, or basic media. In this reaction, it was performed under basic conditions. The resulting intermediates underwent dehydration to introduce an alkene functional group. To complete the synthesis, a carbonyl group needed to be installed on the double bond. Wacker oxidation is typically used in such cases. However, in this specific reaction, it led to the anti-Markovnikov addition, placing the carbonyl group incorrectly due to steric hindrance. To address the regioselectivity issue, the group used an iron-catalyzed Wacker-type oxidation instead of palladium, which successfully produced the desired product. Finally, the target molecule was achieved through double O demethylation using a Lewis acid.